In this video, we're going to talk about section 11.3, and it's about volume and surface area. But I want to kind of take a minute and first talk about the concepts. So let's talk about volume. Now, we've talked about area in section 11.2, and the concept with area kind of works like this. Let me just draw a rectangle, kind of make this as easy as I can. All right. And the idea is, let's say this rectangle is measured in inches or something, right? The idea is I try to figure out how many 1-inch squares I can fit inside the rectangle. And that's area. So volume is similar, except this time I'm going to draw a box. All right. So there's a few ways to draw boxes visually, and I will be drawing them a few times. So let's just kind of go through it. Typically, you can kind of draw almost like a parallelogram, a rhombus, something like that. And you want to draw lines coming off of that. And then you kind of mimic the front box. There you go. That's as good as it's going to get. That's fine. Okay, so for this one, instead of 1-inch squares, because we are in 3D, we're talking about 1-inch cubes. And I'm interested in how many 1-inch cubes I can fill in this box. Now, I'm bringing this up because from a standpoint for teaching this visualization is extremely important. And it's so important that it's practically required that you look at using 3D building blocks to actually talk about volume and using paper squares or some sort of squares to talk about area, just so that difference is very clear with the hands-on. For us, we'll just kind of emphasize the difference in notation. So inches squared for area, and then for volume, inches cubed. So using the square on the area, cubed for volume. Okay, so I want to do an example that they kind of discuss in the book, because again, it's kind of important to make sure we understand the visualization from this. So if we have okay, drawing a cube again, or sorry, a rectangular box again here. And I want to make it a little bit longer. And I want it to have, oops, the equivalent of three cubes on top, on the side, and then 2 cubes high. Okay, so you would say, all right, what is the volume for this rectangular solid? Okay, and the idea is you're supposed to count up how many cubes you see. So each cube, right, is one of these. So if I'm counting up all the cubes, I would have 1, 2, 3, 4, 5, 6, 7, and then there's one in the back corner there, 8, 9, 10, 11, 12 in the back corner. So 12 cubes total. Now, I bring this up and you're like, okay, that's not complicated. For those who are able to visualize, no problem. But when this question was posed to students on a math exam, for those students, only about 6% of 9-year-olds answered correctly, 21% of 13-year-olds answered correctly, and 43% of 17-year-olds answered correctly. So the vast majority of students do not understand the visualization for volume, in particular with cubes. Okay, so It's super important to give time to build that understanding in students. Okay, we'll come back and talk about surface area in a bit. Before we do that, I actually wanted to look at the problem opener. So this is on page 754. And if you want to pause and turn to that, that way you don't have to worry about trying to draw what I'm going to bring in from the book. It'll make it easier. Okay, so here I'm going to go ahead and I actually pulled this from the book, so I'll paste it in just so we can look at it. Like I said, when you're working on your own notes, it might just be reasonable to open your book and refer to it. Picture is so big that I had to squeeze it down. Okay, there we go. So there's the problem opener. And they ask to figure out what the pattern is and use that to figure out what would be in the 10th figure. So I just wanted to kind of pause for a second and let's look at counting the cubes up and discuss that really quick, just so we feel comfortable with what they said is the answers for each object. So the first object, I hope we see that there is 1 cube here in this stack, and then another cube right below it. So 2 cubes, 1 cube here in the middle, and then another 2 cubes here on the side, for a total of 5 cubes. So take a second, look at the cubes then for the second one and see if you agree with what they said, because they do actually tell you how many cubes are in the second one. And I kind of like to just cheat a bit and make my life a little bit easier as best I can. So when I'm looking at this first tower, I'm just kind of looking at this little cubit block here. I see that I have 4 squares on the top, 3 squares on the side. So that to me then says that this whole thing is made up of 12 cubes. So if I have 4 cubes stacked up to make this top piece here, these are the 4 cubes that, stack up to make the top piece. And I have 3 stacks of them, right? That's 12 total. And that then is also the exact same as this one back here. So there's 12 total cubes there. So 12 plus 12. And then down here, this little opening that doesn't have stacked cubes is another 4 cubes. So 12 plus 12 plus 4, 24, 28 cubes. And again, they gave us that answer. Okay, so looking at the last one then here, what we have is a total of 81 cubes. I would encourage you to take a moment again to kind of make sure you follow it and understand why there's 81 cubes there. But I do want to kind of focus in on the pattern we see for each figure, because that's going to help us figure out how many cubes there would be in the 10th figure. Okay, so here's the pattern I'm noticing. So I have a larger cube now, square cube here. I have 9 cubes total that make up this stack up here at the top. And then I have 1, 2, 3, 4 of them stacked up. And that repeats over on this side, 1, 2, 3, 4. So I have a 9 by 9 cube in a stack of 4 twice. Then that same 9 by 9 cube is right here. You know, I can't really see it, it's behind, right? But that's a single stacked 9 by 9 cube. I'm sorry, I'm saying 9 by 9 and I should be saying 3 by 3. Wow, what a doofus. 3 by 3. 9 total. Okay, there we go. So this should add up to 81. So let's see. 9 times 4 is 36. 36 times 2 should be 72. It is. Okay. Wow. And then not plus 3, but plus 3 by 3, which is 9. And 72 plus 9 is 81. Yay. Okay, that just was failing all over the place. That's fine. So if I'm going to visualize what the 10 by the 10th one is, it's going to have a 10 by 10 square, right? The top is going to be, I'm not going to draw it out, right? But it's going to have 10 by 10 here, okay? Now, as far as the stacking goes for each of these towers, it looks like the tower is always stacked one higher than that number. So this is a 3 by 3 square up here, a 3 by 3 squared, and it's a stack of 4 tall, okay? Here we had a 2 by 2 square, and it was a stack of 3 tall. Here we have a 1 by 1 square, and it was a stack of 2 tall, okay? So I'm expecting the tower to be a height of 11. So here's what I'm thinking. I'm going to have a 10 by 10 tower or 10 by 10 square that has 11 of those stacked. So 100 cubes with 11 rows or stacked up 11 of them, okay? Times 2 because there's 2 towers since it's a U shape. Plus we have this middle one here that's always in the middle. It always looks like the exact same square as the others, okay, but it's only stacked up one high. Same with right here. 3 by 3 right here in the middle, stacked up one high, okay? All right, so plus another 10 by 10. All right, so let's figure this out. That's going to be 100 times 22 plus 100. So that's 2200 plus 100, which is 2300. And that's correct. So the visualization of the cubes and being able to kind of 3D visualize what's going on there is a skill that's super important to work on with students. And like I said, it's really important to actually take some time to build that skill set with actual visualization. Okay, so let us continue. Okay, so let's look at a slightly different type of scenario for volume. So now we kind of understand the concept behind visualizing volume. I want to kind of come back and talk about the only other piece we really should discuss about volume, and that is converting. So since we went through a whole section on conversion, we do expect to have conversion. We have it with area, but we also have it with volume. So let's figure out how many cubic inches are in 1 cubic foot. Okay, so here's how that would work. I think the easiest way is to start with the conversion between inches and feet. So I have 12 inches equals 1 foot. And I want to have a cubic foot. So I'm going to cube it, literally raise it to the power of 3. But I'm going to do that on both sides. And I'm going to grab my calculator and plug in 12 to the 3. And that gives me 1,728 inches cubed equals 1 cubed is just 1 feet cubed. All right, and if you don't know how to use your power button on the calculator, you can always reach out to me. Send me like which calculator you have or a picture of it, and I will tell you how to do it if you have trouble with that. Okay, so here, let's look at another one. Let's do how many, here we'll do a metric one. How many centimeters or cubic centimeters, sorry. How many cubic centimeters are in 1 cubic meter? Okay, so grab my conversion. 100 centimeters equals 1 meter. And since I want them to be cubed for volume, I literally cube them. So that's going to be 100. So 1, 2, 3. Okay, so 1 million centimeters cubed equals 1 cubic meter. Okay, So that's how we kind of figure out how many are in the cubic conversion. But then if like we're given a number, like let's say, excuse me, I'm sorry. Let's say I'm asked how many cubic, or here, actually here, let's write it as a conversion instead. So let's say I'm trying to figure out how many inches cubed equals 1.4 feet cubed. Okay. So in this case, because I happen to know this fact up here, all right, that I can use it. So let's write it down. 1728 inches cubed equals 1 foot cubed. So if I want 1.4 feet, that means I'm literally going to multiply this by 1.4 on both sides. And 1728 times 1.4, I get 2419.2 inches cubed equals 1.4 cubic feet. So that's kind of the basics of how we do conversions with volume. Okay, so I do want to like take a moment and mention surface area. So we have talked about area, which means surface area is not a big stretch past the idea of area. Okay, but there are just a couple things I want to kind of emphasize. So for surface area, let's go back to the problem we saw at the beginning, the example we saw when we started talking about volume. So here, let me draw my 2 by 2, and then, oops, a little bit crooked. Not that that matters all that much. Okay, and then there's 3 of these. There we go. All right, did my best. And I know you guys do your best too. Okay, so what would the surface area of this be? So this time we'd be counting the actual squares, how many squares we see on the outside of this box, okay? So I know that for the top, we'll call this top, that I see 1, 2, 3, 4, 5, 6 squares, which means I would actually have a bottom as well. So there's a top and a bottom, right? So if I have 6 squares here, I should have 6 squares here. Okay. For this side, we'll just call it side. I have also 1, 2, 3, 4, 5, 6 squares there, which means there's a back side to this that I cannot see back over here on the back end. And that side will also have 6 squares. Okay, and then we'll go ahead and look at the front. Talking about this front side here, which I'm referring to this front. And here we have 1, 2, 3, 4 squares. That's not how you spell front. That spells from. That's very weird. Okay, but there's also a back. And the back is also going to have 4 squares. So 4 squares on each of those. I don't know why I haven't been consistent with putting colons, and it's really weird that I put it down there. Okay, there we go. So add those all together. So for the sides, there's 2 of them. For the top and bottom, 2 of them. And then the front and the back, 4 of them, which gives me 12 plus 12 plus 8. And that adds up to 32 squares. So that would be the surface area, whatever the square's measurement is. Okay. Okay, so let's just take a moment and compare a couple of figures. So this figure is drawn in example D, or hold on, I'm going to look for a second. Actually, take a moment, make sure I'm saying it. Yeah, example D. This particular example I'm going to draw here. And if you want to open to example D, that's on page 758. Okay, so that is, it's got a square top That's 3 by 3. Okay. And that's a terrible line. Let's try that again. Boom. All right. And then it's stacked 2 high on either side. So 2 high. There we go. Okay. And then on the try it, on the exact same page, the try it 11 3.33. I'm sorry, 11.33. I think I said that weird. That one is a flat rectangle, only 1 cube high, but it has 6 on the top. And then, oops. And then it goes 3 this way. There we go. Okay. And if you count up the volume for each of these, they both have a volume of 18 cubes. Because the first one has 9 in the first square, right? And then 9 in the bottom square. And by square, I'm referring to the stacked square here. This top square and then the bottom square. Okay, so a total of 18 cubes. And this one also has 18 cubes. It's flat, 6 by 3 and 1 high. All right. And yeah, it's 18 cubes as well. Okay, but let's compare the surface areas. That's the whole point. We're going to compare the surface areas. So I'm going to kind of count this out, and then rather than write a bunch of stuff, I'm going to try to make it a little easier. So the front here, 1, 2, 3, 4, 5, 6. The front has, oops, I was going to do from again. That is so weird. Has 6, and it's mimicked in the back, which we cannot see in this picture. Then we have the top. The top has 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's mimicked by the bottom, which we cannot see. And then the side that we see showing 1, 2, 3, 4, 5, 6. And there's a back side that we cannot see. All right. So we'll add those all together. Let's see. 12 plus 12, 24 plus 18. So I have 32. No, sorry, 42. 42. Okay. Surface area is 42 squares. Okay, now let's compare that with the surface area over here. So this one, a little bit easier to see because 1, 2, 3, 4, 5, 6 by 3. So there's 18 squares on the top here. So the top, or yeah, the top has 18. Same with the bottom, has 18. The front, up here, 1, 2, 3, 3 squares. And there's a back that we don't see. And then the side has 1, 2, 3, 4, 5, 6 squares mimicked on 2 sides. Okay, back side as well. Add those together. Okay, so let's see. That's 36 plus 6, 42 plus 12. Okay, I'm getting 54. Oops, 54 squares. Okay, so just because 2 figures have the same volume, meaning they were built on the same number of cubes, the surface area is definitely different. Kind of makes sense too, that the big flat box is going to have more surface area than the square box, okay? And it makes sense too when you're talking about, like, if you were to make a box from this, like with cardboard, it would be less cardboard to make than this box. This box requires more cardboard, okay? So we kind of get an idea of the relationship between how surface area works versus volume and the concepts between them. So the next video, you're going to get actual formulas for finding volume and surface area.